Yeah, this is just from last year. I didn't have service through most of it. I mean, I did, just not like.
Wait, so you had service of like fishing and stuff, so you can see pictures of it and stuff? Or?
Yeah, so they had like a.
A router or something?
Yeah, they had a router out there.
Oh my goodness. All right, well, +1 vertical. That's looking pretty good, isn't it?
Yeah.
Okay, so then our integral is a lot of writing.
That's the part I hated about this.
Okay. And then obviously the numerator cancels. So that's nice. And then natural log of natural log of 1 over u is what? I said integral of natural. You know what I mean. Good grief.
Natural log of next to the
Yeah. Okay, so that one is C, it looks like. But thinking of other strategies that we have used, what else could you have tried? This worked. It worked good.
I was trying to divide it.
Like long division? Okay. You could have potentially considered factoring and then canceling beforehand, just to simplify, right?
I guess you could do that.
This one, obviously the numerator is fine, but denominator, I'm trying to think of factoring by grouping. I don't think that's not going to work.
So usually with like the U substitution, usually I look for, like, I look at the numbers and if their powers are like one more. So like on the bottom, it's like one more and one more and one more than everything on the top. Then you can, when you take the derivative of it, it'll make it equal.
Yeah, I agree. So it's a good strategy. But just knowing going in that we have lots of strategies, sometimes you just have to try one, and in this case it worked out. But I think this is one, I probably wouldn't have looked at division just because dividing a smaller exponent by a larger it doesn't really work.
I was just like here, like, oh, it's gonna work.
Yeah. But it's not a bad thing to keep in mind for sure. And then of course just simplifying beforehand, we've seen those kind as well. So, but you worked, and I think that's a good thing to keep an eye out for when your numerator powers are just one figure. How did the problems go from Friday? It was 1, 4, 1, 2, 4, and I think 7 on 6, 10.
Oh, yeah, those are good. I did it in my phone.
You did?
Yeah.
Did you check them?
Yeah, I did.
Did you do them?
I
Okay.
You said 1, 4.
1, 2, 4, and 7, I think is what I said. Because we hadn't quite finished completing the square stuff. So,
Okay.
well, we had done a little, but we hadn't quite finished it. So.
You want me to do those?
Well, yeah, we'll just lump them into tonight. We'll do some more of that section tonight. Actually, yes, do those. We're gonna talk about 614 briefly, which is the last stuff, and then there's problems to practice there too. So yeah, do them. Anyway, so let's go back to that last example that we didn't get to on Friday. So just, Aiden, since you were gone, these are just more strategies where we learned that we could do long division
Okay.
to simplify. And basically it's just a rewrite of the integrand in a way that, like this one, if we divide by x minus 2, then we have these three of the terms are just directly integratable.
Yeah.
And that last term we can just do a u substitution just on it. And same thing over here. We created a similar situation. Instead of trying to integrate this weird quotient. Does that make sense?
Yeah.
Did you ever do that last year?
I think so.
And then same over here. So it's just a strategy, but this was completing the square. So if we complete the square on that denominator, remember that we added the part to complete the square, so then we had to subtract it off in the same denominator. And then allowing us to do, in that case, inverse tangent. So we had started on number 4 by saying that we thought it was probably going to be what form? Inverse sine, because we see a square root.
And a minus.
Yeah, so let's, that needs to go up there. So let's go ahead and complete the square on the denominator part that's inside. I'm going to factor out that minus real quick. Actually, I haven't written all that first. Okay, so what are we going to plug in there to complete the square? Yeah, so b, which is 8 over 2 squared. Okay, and then it's plus, but really minus, since I factored out that negative, so we really have to add that same thing. Okay. Okay, so we get minus 15 plus 16, so we get plus 1. Okay. Now, let's go ahead and do an intermediate step of plugging that in so we can see our progress. And it's nice to put the 1 first. And it does definitely look like sine. Well, inverse sine, I mean. But what will we have to do at this point?
Substitution.
Yeah.
Wouldn't it be x plus minus 4?
Yeah. I wrote it wrong. Here we go. Anyway, so dx equals du, since our derivative is just 1. Okay. Plus plus 1, just randomly, plus C. There. Anyway, and then from there, we'll just plug in x minus 4. We need to do here on one of those days because Dylan was forgetting his plus C.
Oh.
Should have punched.
Yeah. All right, well, so completing the square, just know that you might have to combine that with U substitution, and probably will have to.
What's the 8 over 2?
Remember, so b over 2 squared is how you complete the square.
Oh, yeah.
So I should have written -8 here. That was my fault. That it didn't make a difference in the sign of what we
Right.
did, but I should have written it anyway. So yeah, so b
B
over 2 whole thing squared completes the square.
Okay.
So we add it in here with the x squared, but usually
But then you
subtract
have to
it.
subtract
Take
it.
it off. Yeah.
Yeah. Okay.
Yep. Any questions on it? I think again, just like with all these, it's going to be seen to do that is the hard thing, right?
Well, especially for these ones, 'cause it's definitely kind of tricky.
Yeah. They do, at least they don't, I can't fit it, zoom out a little bit. At least they don't look like the division ones. At least we won't be mixing it up with those, I don't think.
Yeah.
But, I mean, you might think, oh, hey, I could use substitution that initially, but of course nothing would cancel. So I'm hoping that with some practice it'll stand out a little bit better, but it'll take some time. The next 3 sections are BC topics. I want to come back to, hopefully we'll have time to come back to 611, which is integration by parts. But we're going to skip it for now to make sure we have time to get through other things. Did you use that a lot? Do you remember on your test? Probably hard to remember that. It's good. Integration by parts is a good thing to know. But so the last section that we have to cover for AB is just 14, which is kind of like the end of the differentiation unit where we just had, we kind of just reviewed our methods, honestly. So, and I think the goal of this, of course, is to pick the best strategy, but I think with that, it's just practice to get there. But let's fill this out together. See if we can remember. And the bullet points, 1, 2, 3, 4, 5, 6, 7, might not include like all the little details that I would like us to know, like the inverse, or excuse me, the integral of like tangent or whatever, right? Or cotangent. So if we have to flip back and forth, that's fine.
Well, the first one thing is the inverse power rule.
Okay. So we're gonna definitely need more lines, but I'm totally fine with that. So that was, you remember how to write it?
Yeah, it's x to the n plus 1 over n plus 1.
Good. Okay. And then how about basic trig? Man, this is not enough room. I'm gonna zoom in a little bit. Okay, so how about integral of sine? Integral of, did we do negative sine, negative cosine, or just cosine? Just cosine. Which is what? Sine? Okay, and of course I'm not writing all the notation, it's just review of what the process would be. Okay, how about, because I know we're going to want to write our rules, some of them in here. So I'm going out to the side. What about integral of like a to the x?
Oh,
x would be 1 over, a to the x over ln of a, because it's 1 over, and then the integral of that would be ln.
Because if we took the derivative of this, remember the derivative is a to the x natural log of a, but we'd have to cancel off that natural log of a part. So we put it in the denominator. And then let's just stick in there with the e to the x is just e to the x. Our favorite one.
It's like simple, but it's like, there's like a lot of e to the x in here.
True. Okay, let's see if we how many of these inverse trig ones we can do. Not inverse trig, sorry. Like secant. What are those called? I forgot.
Like,
Okay, the inverse.
They're not inverse. They're
advanced trig?
no, they have a name. For some reason, I'm drawing a blank right now.
Weird.
Complementary, the complementary like ones. Anyway.
Weird looking trigs.
So, and I think we all know them by sight, but I don't know that we know them by memory. So did we have one for secant squared?
Would be tangent. Yeah.
Tangent. Yep.
Then,
I think we had one for secant tangent.
right.
I need to write my x in there. Hold on. It was.
Secant of x.
Okay.
Right. Yeah.
Yep.
Negative cosecant squared.
Just cosecant. Well, we have this one. Maybe you're talking about a different one.
Cosecant
Cotangent. It should have been
tangent. I was
cotangent.
like, how do you do that?
Yeah. Cosecant, cotangent.
You just cosecant.
Yeah. All right, and then you said cosecant squared.
Yeah. Negative cotangent. Negative.
I think we're doing good.
Yeah.
Okay, then we had now we're into the inverses, so
Inverse of
which
that's
one is that?
tangent.
Good.
Inverse. Already had this
Okay.
one. Square root of sine. Inverse, yeah, that's sine. Inverse. And then,
That was all we wrote.
no, we had inverse cosine, which is.
Are you sure?
Yeah, I'm pretty sure. Yeah, I thought we had that one because it's the absolute value of x. Yeah.
No.
No, inverse secant. Oh, that's.
Oh, okay.
Oh.
Yeah, inverse cosine would be. It's the same as sine, only with or sine with the negative sign.
Oh, yeah, that's right. Inverse secant is the one with the absolute value. Yeah. Square root of. Yeah. Oh, no, it's the x squared minus 1.
Yeah, that one we reverse. Good.
And then cosecant would just be negative of that.
Yep.
Okay.
And tangent is negative. So all the C ones, cotangent is just -1, cosine is -1, and cosecant is -1.
Sweet. That
So
makes
that's
sense.
nice, yeah. All right, rules. Rule wise, we had big one, which was U substitution. Actually, before I write that, let's write properties. These kind of problems can sometimes be tricky, even though the properties were simple. Do you remember?
Yeah.
If you won't draw that the way I like it. Good enough. So things like, if we have a constant, what can we do with that?
Oh wait, no, you integral. You add x. Yeah, you just add x.
Well, no, I meant if we have a constant multiple and we're taking the integral.
You can just take it.
Pull it out front, right?
Oh, yeah.
Okay. We had the sum and difference, where we can just split them up. We had, do you guys remember the ones that were those two? Do you remember the absolute value thing? Okay. How about, what do you do for this one? And I don't remember if I'm writing the way that we saw it. Let me check. Six. There it is. That wasn't 6. What was it?
How's it going?
Good, how are you?
Good.
We're packed in here.
Yeah, there's a lot of kids in here. Fair enough. You guys have a good day.
You too, thanks for checking in.
Yeah.
Where? I'm not seeing where that was.
I remember we talked about it, but I'm not sure it was in the packet.
I wonder if it was when you were just doing sums. Do you guys remember the definite integral formula? We should write that down just as a review.
Oh, S plus B minus F of A. Like big F.
Yeah.
All that stuff, yeah. Alright, well, let's just leave it like that and I'll find it and edit it down the road. Okay, now we have one of the biggest ones, biggest in terms of use. Use of use. Oh, that's funny. Okay, and then what else? Long division to simplify, we had completing the square.
What I hate.
Oh yeah, I forgot Dylan's nightmare is long division. Okay, what else can we stick on here that's helpful? I would say that we should put, actually before we do that, let's double check.
I wrote-
Yeah, we got all those, those are all.
The integral of 1 over x is
There's natural log.
ln, yeah,
Yeah.
natural log of absolute value.
Put it up here by the E. Good, that's definitely a good one to have on there. Seems to come up all the time. Alright, I think we got most of it, but I think it would be good to write that definition formula.
You going to set the,
What?
talk about the definite interval.
Oh,
That thing?
I remember that thing.
I have to look at it.
Wait, are we gonna use the BC thing?
Oh, I guess, yeah, no, we're not. So we could write it over
Yeah,
there.
we could just write it.
Good job.
What do you guys do?
That's all the hard.
That's right. I'm looking.
Is it B?
B minus A, oh yeah.
Minus
B minus A over N is
over
the,
N.
that's the width.
Times F of A, is it not? That's like F of A,
A plus.
plus B minus
minus-
A over N.
Okay.
Okay.
Yep. And keep in mind that when we were doing AP problems, we often saw that part at the end. B minus A over N part
Yeah.
was at the end. Okay. And then what is N?
And is your
Is the width, is it not the width?
No. The width is this B minus
Is
A
B
part
minus.
over N part.
and is your
It's the number. It's which one you're on, you know what I mean?
yeah,
Like the,
Yeah, so N is the number of subintervals.
yeah.
yeah.
That word.
And then what is this?
That's
The
the
whole
X
thing.
value at N subinterval,
Yeah.
or K at K subinterval.
Yeah, so in here, that's the X value of the kth subinterval. So, but this whole thing is the height.
Oh, yeah.
Okay.
Okay.
How about the fundamental theorem? Let's put that on here.
Not fun.
That's such an important name.
I know,
I
isn't
feel
it?
like
It's like
It's
the,
like the fundamental, it's like the base.
yeah,
fundamental theorem of calculus, and it's just F of B minus F of A.
yep. It's a lot of good stuff. I can't think of anything else. I mean, we started the unit with Riemann sums. Do you want to put any of that on here? It'd probably be good to review. Let's see. What is how do you do a left Riemann sum without a graph?
Not a
Take-
graph.
Yeah.
Take your
Well, don't you use the
B.
don't you take the limit notation and do K minus 1?
So you take the beginning of each interval, right?
Right.
Plugging the beginning in.
Y value at the beginning of the.
Yeah. No, I'll just say interval, subinterval, same thing. Okay, so if you had a table, maybe you would just plug in the left values of each subinterval. What if it was like kind of a description, like what's the left Riemann sum from 5 to 10? Let's see. let's see, 5 to 9 with 4 subintervals. That would be kind of the same. No, it's not quite the same. Yeah, 5 to 9 with 4 subintervals. So what would you plug in?
You would plug in, 5, wait, 6 minus 5.
8, 9.
So you'd plug in 5, 6, 7, 8
Yeah.
for left Riemann sum. And what would you plug in for a right Riemann sum?
It would be 6 and 8.
6, 7, 8, 9. And then midpoint would be in between those, etc.
Right.
Okay. Okay, and then for things like under or over estimates, we can just sketch a picture. Are we good with that?
Yeah.
For concavity. Well, which ones use concavity?
It's
To determine
the left midpoint and trapezoid.
midpoint and trapezoid had to require concavity.
Oh.
And remember we figured out, because I kept struggling to draw it, like if you really emphasize the interval, instead of trying to do little ones, do like one huge one, it makes it more obvious. Does that make sense? So concave up, was that over or under? I'm trying to draw a trapezoid. Okay. Anyway, and then for left and right, those ones were easy. Because you could just draw like a line. Remember that?
Yeah.
So that didn't depend on concavity, but increasing or decreasing. So I think it's worth just drawing a picture. If you get asked that. I think that's about it. It's a lot of stuff. A lot of really, really important stuff. For sure.
Yeah.
Oh, I forgot this though. That whole section on the derivative stuff. So that whole thing. That was the other part of the fundamental theorem. Remember that? I guess the notation is a, not 0, so a to x. But 0, if a is a constant, any constant would be fine. But so what was we haven't done, I should have put a problem up recently where, what if we had like f, I'm just going to make up actually 2 new ones, h of x, g of x, and f of t dt. And we're taking the derivative of that. Do you remember what to do?
Just do, wouldn't it just be f of g of x minus f of h of x?
No, it's f of g of x plus g. No, f prime of, hold on.
I know what you're trying to say, but I'll wait for it.
Yeah, you can. It's, f prime of g of x plus g prime of x. And then minus. f
Not
prime-
plus though, it's just times.
Oh, times. And then minus f prime of h of x times h
H prime x, it's a dot right there. Good. So we often had to do the chain rule on that. But remember the idea of that section was the derivative of an integral just cancels.
Yeah.
But we can plug in, like in this first one, I should write it also, is f of x minus this one, which is just 0, if it's a constant. All right, and then up at the top, what should we write?
For
Never
Oh,
forget the C. Okay.
unless it's a definite.
Yeah. True. So maybe I'll just put for indefinite here. Okay, and then remember this stuff goes back to Unit 5 where we were talking about maxes and mins and either absolute or local and points of inflection, but it was always just one layer ahead of what we learned in that unit if it was for an integral. By the way, we saw, I don't want to pull it out, so I'll just try to remind you, but do you remember the problem on the last quiz? It was towards the end, that it was a limit problem.
Oh, yeah.
It was like limit as x, I don't remember, it was
X
x
approaches
approaches 6, I
3
think.
or something.
And then it had an integral that became 0 over 0.
Okay.
Okay, I don't know what this was down here, but
It was like g of x minus 6.
let's say it's this. Okay,
Oh,
Yeah.
let's just make something up. And then, yeah, something up here that became 0. And so we talked about it while you were gone, that's why I'm bringing it up. But don't forget that when you have a 0 over 0, what can you do? Just find the limit.
Oh.
Or infinity over infinity, either one. No. If this was I remember the word, it just came to me. Remember I drew a blank. It's indeterminate.
Yeah.
The indeterminate form like this, no, you can't just say it's 0.
Oh.
So what we ended up needing to do is take the derivative of the
Of that
integral.
one, and then take the derivative
Yep.
at the bottom until you get something.
Yep.
Okay.
So that could come up too.
Oh,